this video, we'll be exploring the use of the capillary viscometer, specifically in its application for measuring the molecular weight of various polymers that are dissolved in solution. So let's begin by taking a look at the construction of the capillary viscometer. Here at the bottom is the reservoir bulb where the sample will be filled through this top tube here. The sample is then filled between the two brown lines marked at the top of the reservoir bulb, and at which point suction will be provided to the top of the viscometer. The smaller bulbs above the capillary are filled, at which point the sample is drained and the time is taken, and we measure how long it takes for the sample to travel between the two lines. To begin our experiment, we'll be dissolving PHA biopolymer in varying concentrations into chloroform. We'll be dissolving 0.5, 1, 2, and 3 milligrams per milliliter into chloroform. You want to make sure the polymer is well mixed in solution, and you want to make sure that none of the polymer remains stuck to the sides or bottom of the vial. To take a measurement of a given sample in the capillary viscometer, we'll begin by using the pure solvent chloroform and filling the bulb through the fill tube. We'll continue filling the solvent until the bulb is filled between the two lines. At this point, we will apply suction to the capillary to fill the measurement bulb. In this case, I'll be using a transfer pipette. Once the bulb is filled, we will release the suction and time how long it takes for the liquid to drop between the two lines. I've taken the 4 polymer solution samples here and sped them up, and we will take a look at how long it takes each. After each measurement, record the time taken for the sample to travel through the capillary. And then you just want to make sure that the viscometer is fully rinsed out with the solvent and air dried. Once we've taken the time measurement of each of the polymer solutions, we will organize the data into a table as shown here. We can begin our calculations by determining the kinematic viscosity. This is done by taking the time measurement and multiplying it by the viscometer's constant, in this case 0.00099. From here we can calculate the dynamic viscosity by multiplying the kinematic viscosity by the solvent density. In this case, that's 1.49 grams per milliliter for chloroform. Next, we can determine the relative viscosity. This is done by taking the solution time and dividing it by the pure solvent time. And finally, we can calculate the specific viscosity by taking the difference between the solution viscosity and the solvent viscosity and dividing it by the solvent viscosity. We can then determine a couple of calculated values, the natural log of the relative viscosity divided by concentration and the specific viscosity divided by concentration. These will be used in a plot, and we will determine what the intrinsic viscosity is of this particular polymer. So shown here is the plot of these two calculated values plotted against the concentration of each solution. Once we see that we have a good fit on both of these plots, we should also see that they have the same y-intercept. You can see that is 0.1192 and 0.1191. This value is the intrinsic viscosity of this polymer sample. This procedure of measuring the viscosity of multiple concentrations of polymer and then plotting to determine intrinsic viscosity will be repeated for several samples of polymer of different known molecular weights in order to generate a standardized curve. And I've repeated this process for 4 different polymer samples ranging from 137,000 to 1.2 million Dalton's molecular weight. I have shown here the intrinsic viscosity I've determined and calculated the natural log of the intrinsic viscosity and the natural log of their molecular weight. Intrinsic viscosity is related to molecular weight through the Mark-Howink equation shown here. It shows that the intrinsic viscosity is related to molecular weight through the constants K and A. So by taking our polymers of known molecular weight and plotting them on a log-log plot with intrinsic viscosity, we can determine these constants. In this case, the constant A is the slope of this line, so 0.6695, and negative 0.539 is the log of K. Now that we've established these constants, K and A, we can measure polymer samples that have an unknown molecular weight, and by measuring their intrinsic viscosity and applying these constants, we can determine their molecular weight. And this is valuable because a lot of traditional molecular weight measurements are time-consuming or require expensive instrumentation that's not readily available. In conclusion, in this video we've covered the use of the capillary viscometer to measure the viscosity of polymer solutions. We've also looked at how to take these measurements and determine the intrinsic viscosity of a given polymer solution. And using that data, we've discussed how to use the Mark-Howink equation to determine the molecular weight of a given polymer sample.